The outer solar system is supposed to be flat, not perfectly flat. There are small wobbles, tiny gravitational nudges traded between planets over billions of years, but flat enough that every major body orbits within a narrow disk, like grooves pressed into the same record. That's not a rule anyone invented. It's the leftover geometry of the cloud of gas and dust the solar system formed from, and it should have held. It hasn't. A team at Princeton ran the numbers on a large collection of trans-Neptunian objects, the frozen bodies that drift in the dark beyond Neptune, and found that their orbital plane is tilted, not by a fraction of a degree, by 15 degrees. That's not a wobble, that's a warp. And a warp that large, at that distance, doesn't happen on its own. To understand why 15 degrees matters, think about what it takes to tilt something at that scale. These aren't small rocks being nudged by a passing comet. They're distant objects with deep solar orbits, and the only thing capable of bending those paths in a coherent, consistent direction is sustained gravitational influence from something massive. The disk isn't randomly scattered, it's been pushed, which means something pushed it. The Princeton team's inference is that a previously unknown planet is sitting somewhere between 80 and 200 astronomical units from the Sun. For context, Neptune orbits at about 30 AUD, so we're talking about a body 2 to 7 times farther out than the most distant recognized planet in the solar system. It's rocky, somewhere between the mass of Mercury and the mass of Earth, and it has never been directly observed. They're calling it Planet Y. Let that sit for a moment. A planet-sized body orbiting our own sun that we simply haven't seen. The instinct is to ask how that's possible, how something that large, that close in astronomical terms, could have gone undetected. The answer is distance and darkness. At 200 AU, even a body the size of Earth reflects almost no light back toward us. It's not hiding. We just haven't had the tools to look hard enough in the right places for long enough. Until very recently, we haven't. But here's what makes the warp so compelling as evidence. It's not one anomalous object with a strange orbit. That's easy to explain away. A single gravitational slingshot, a long-ago near miss, a statistical fluke. What the Princeton analysis found is a pattern. Multiple objects, orbiting independently across a wide stretch of the outer solar system, all tilted in a way that only coheres if something is out there pulling them into alignment. The signal is in the coherence. Gravity leaves a shape in the paths of everything it touches, and the shape here points at something real. The question the rest of this video is built around isn't whether the warp exists. The data on that is solid. The question is what made it, and to answer that, you first have to understand exactly what the math is actually saying about the size and location of whatever is out there. So what is the math actually saying? Not the headline, the mechanism. Because the inference here is more careful than it might look from the outside, and understanding it changes how seriously you take the conclusion. Start with how gravitational inference works in the first place. You can't see a planet directly at 80 to 200 astronomical units. At that distance, even a sizable rocky world reflects almost no sunlight. It's effectively invisible to current telescopes. But invisible doesn't mean undetectable. A mass that large, sitting in one region of space for billions of years, exerts a continuous gravitational tug on everything nearby. And that tug leaves evidence in the orbital paths of objects you can see. Think of it like this. You're watching a crowded intersection from far away, and you notice that every car coming from one direction keeps drifting slightly right before it straightens out. You can't see the pothole, but the pattern in the cars tells you exactly where it is. The Princeton team applied a version of this logic to a population of trans-Neptunian objects, small, icy bodies in the outer solar system whose orbits are precisely mapped. What they found is that the orbital plane of this population isn't flat relative to the rest of the solar system. It's tilted, about 15 degrees. And crucially, the tilt isn't random scatter. It has a direction, a coherence that implies a single gravitational source pulling the population toward a consistent orientation. Now you plug in the physics. For a body to produce a tilt of that magnitude across that population of objects, at that range of distances, the mass has to fall within a specific window. Too light, and the gravitational influence washes out. You'd see no coherent tilt at all, just noise. Too heavy, and the warp would be more dramatic, and the affected region wider than what's actually observed. What fits? A rocky body, somewhere between the mass of Mercury and the mass of Earth, orbiting between roughly 80 and 200 astronomical units from the Sun. That's the sweet spot where the numbers stop being a guess and become a constraint. The warp is a measurement. The mass range is what the measurement demands. There's one more layer worth understanding: the location uncertainty. 80 to 200 AU is a wide band. That's the difference between a neighbor and something 3 times farther out. The analysis can tell you a perturber exists and roughly how massive it is, but it can't yet triangulate a precise position. Think of it as knowing there's a mass hiding somewhere in a very large room, and you know how heavy it is, but you haven't found exactly which corner it's in yet. That's what makes the next decade so critical. The math has sharpened the hypothesis down to a testable prediction. What it can't do is close the case on its own. Something else has to do that, and that's where the story gets interesting. But before we get there, there's a distinction that almost every headline about this has gotten wrong, and it matters. Here's the distinction almost every headline has gotten wrong. Planet Y and Planet 9 are not the same hypothesis. They're not competing names for the same object. They're 2 separate anomalies, pointing at 2 separate suspects, in 2 completely different neighborhoods of the solar system. Planet 9, the hypothesis that's been circulating since 2016, is a gas giant. Something in the Neptune to Uranus class, maybe 5 to 10 Earth masses, thought to be orbiting somewhere between 400 and 800 AU out. The evidence for it comes from a different set of observations entirely, a clustering in the orbits of distant trans-Neptunian objects, small icy bodies in the outer solar system, whose paths seem to be herded together in a way that random chance doesn't explain well. The inference is a massive, distant shepherd, big, cold, and extremely far out. Planet Y is something else. Rocky, Mercury to Earth in mass, so we're talking about a fraction of Planet 9's hypothesized bulk. And sitting between 80 and 200 AU, which sounds remote until you realize that's less than half the distance to where Planet 9 is thought to lurk. In solar system terms, that's not the deep wilderness. That's the outer suburbs. The anomaly driving the Planet Y inference is also different. Not a clustering of small bodies. A warp. That 15-degree tilt in the plane that the outer solar system's known objects collectively define. Different signal, different location, different mass range. The math that fits the warp doesn't produce a gas giant. It produces something terrestrial, something rocky and relatively modest, doing quiet gravitational work at a range where we might have reasonably expected we'd already found everything significant. That's actually the part that should stop you. 80 AU is not the edge of perception. We've cataloged objects smaller than a city at those distances. The fact that something massive enough to tilt the orbital plane has gone undetected there, if it exists, says something uncomfortable. Our census of the solar system is less complete than we thought, even in the zones we consider mapped. So if both hypotheses are right, the solar system has 2 undiscovered planets, a rocky one in the outer suburbs doing something to the plane, and a gas giant in the deep dark doing something to small body orbits. Neither one confirms or rules out the other. They coexist as separate problems demanding separate solutions. And that raises an obvious question neither hypothesis has answered yet. Where did Planet Y come from? Because a rocky world sitting that far from the Sun is hard to explain. The inner solar system where rocky planets form is a long way away. Getting from there to here requires a story, and there are exactly 2 serious candidates for how it happened. The first candidate is the one that feels almost cinematic. Planet Y didn't form here. It formed somewhere else entirely, around another star, or in the cold interstellar gap between them, and the early solar system reached out and grabbed it. This is called gravitational capture, and the basic mechanics aren't exotic. In the solar system's first few million years, the Sun was still embedded in its birth cluster, a dense neighborhood of hundreds or thousands of young stars, all close enough that their gravitational fields overlapped. A rocky body drifting through that environment on the right trajectory, at the right speed, could be slowed and bent into a bound orbit around the Sun, rather than continuing on through. Capture. The scenario has a seductive simplicity. It sidesteps the hard question of how a rocky planet ends up 80 to 200 AU from the Sun by saying it never had to travel there from inside. It arrived from outside already moving on a wide, looping path. The solar system's gravity reshaped that path into something permanent. But here's where the story gets harder to tell. Capture sounds common until you run the actual probabilities, and they're brutal. For capture to work, the incoming object needs to lose enough kinetic energy at exactly the right moment to fall into a stable orbit, rather than swinging past and escaping again. That energy has to go somewhere, either into a gravitational interaction with a third body, most likely Jupiter, or into the energy of the encounter itself. The window for that exchange is narrow. Most close approaches don't end in capture. They end in a flyby. Simulations suggest that during the Sun's cluster phase, capture of small bodies, comets, icy debris, may have happened at modest rates. But capturing something with the mass of Mercury or Earth is a different problem. A more massive object carries more kinetic energy, and shedding that energy through a single gravitational encounter is dramatically harder. The odds drop. There's also a timing problem. The Sun's birth cluster likely dispersed within the first 100 million years. That's the window. Once the stellar neighborhood thinned out, the density of passing objects dropped by orders of magnitude, and the probability of capture collapsed with it. Planet Y, if captured, had to arrive during a very specific, very early chapter. None of this makes capture impossible. Unlikely and impossible are different things, and the solar system has 4.5 billion years of history to hide low-probability events in. But it does mean capture isn't the default explanation. It's the dramatic one. The one that requires the conditions to have aligned just right, at just the right moment, once. Which is why the second origin story is, to many planetary scientists, the more compelling candidate. Not a visitor from elsewhere, something that was always ours, and nearly wasn't. The native scenario starts 4.5 billion years ago, when the solar system was not the orderly place it appears to be now. The planets were still settling. The giants, Jupiter and Saturn, were migrating through the disk, and every object in their gravitational reach was being sorted, scattered, or swallowed. Most of the small rocky bodies that formed in the outer reaches of the inner system simply didn't survive that sorting. They were absorbed, ejected, or ground to dust. But some weren't. A body in just the right orbit, at just the right moment in the reshuffling, could receive a gravitational kick strong enough to send it outward, far outward, without crossing the threshold into full ejection. Not swallowed, not lost to interstellar space, flung, parked at extreme distance, in a slow, cold orbit, where nothing would disturb it for billions of years. That's the native survivor scenario. Planet Y didn't come from somewhere else. It formed here, in the same disk as Earth and Mars and Venus, and Jupiter or Saturn threw it to the edge of the solar system during that early chaotic episode. What looks like a mystery lurking at 80 to 200 AU is, in this reading, just wreckage from the solar system's own violent adolescence, a fossil of the reshuffling itself. What makes this scenario compelling isn't just that it's simpler than capture, it's that we have direct evidence the reshuffling was real and brutal. The late heavy bombardment, the period roughly 4 billion years ago when the inner planets were pummeled by impactors, is the scar it left on the rock record. The current architecture of the giant planets is itself the outcome. The NICE model, which reconstructs that early instability, predicts exactly the kind of scattering events that could have launched a terrestrial-class body to the outer system. And here is the part that is genuinely difficult to sit with. Earth was in that same disk. Earth was subject to the same gravitational forces. The difference between a planet that gets nudged into a stable orbit and one that gets flung to 200 AU, or out of the solar system entirely, can come down to timing, measured in tens of thousands of years. One slightly different encounter geometry, one marginally different orbital phase when Jupiter's influence peaked, and the body that got scattered might not have been the one we're now searching for. It might have been us. The native survivor scenario isn't just a hypothesis about Planet Y. It's a reminder that the solar system we inherited wasn't guaranteed. It's the version that happened to survive. And there may still be a piece of the version that almost didn't, sitting out there in the dark, waiting to be found. That piece in the dark, if it exists, is about to get a lot harder to hide. The Vera C. Rubin Observatory sits at 9,200 feet in the Chilean Andes, and it is not like other telescopes. Most observatories are built to stare, point at one patch of sky for hours, go deep, then move. Rubin is built to sweep. Its primary mirror is 8.5 meters across, and it feeds a camera with 3 billion pixels, the largest digital camera ever built for astronomy. The combination means it can image an area of sky roughly 40 times the size of the full moon in a single exposure. Every few nights, it revisits the same patch. Over 10 years, it will photograph the entire visible sky hundreds of times over. That cadence is exactly what finding Planet Y requires. A faint, slow-moving object at 150 astronomical units doesn't announce itself in a single image. It reveals itself by moving, a tiny positional shift across exposures separated by days or weeks. Rubin's legacy survey of space and time, which began in earnest in 2025, is designed to detect precisely this kind of motion. Objects that would be invisible to any previous sky survey will accumulate detections automatically, their paths reconstructed by software comparing thousands of exposures. If Planet Y is where the orbital math suggests it should be, and if it reflects enough sunlight to clear Rubin's detection threshold, the survey has a genuine shot at finding it within a decade. The Princeton team's mass range, Mercury to Earth, produces a range of expected brightness. The optimistic end is well within Rubin's reach. Even the pessimistic end, a smaller, darker object at 200 AUW, falls inside what the survey was built to catch on its deepest passes. But here is the other half of that sentence. If Rubin runs its full 10-year survey and finds nothing in the predicted region, that is not a null result in the ordinary sense. That is a falsification. The gravitational inference pointed to a specific region of sky, a specific distance range, a specific mass window. If nothing is there, the warp needs a different explanation, or the warp itself needs to be re-examined. Either way, the ambiguity ends. This is what makes the next decade genuinely unusual in planetary science. It has a deadline. Not a vague hope that technology will eventually improve, but a specific instrument with a specific cadence pointed at a specific problem, running right now. And if confirmation comes, if a point of light appears in the right place and tracks the right arc, the consequences cascade fast. A confirmed Planet Y would be the first new planet added to the solar system's inventory in over 2 centuries, since Neptune in 1846. It would validate the gravitational inference method as a tool for finding hidden mass anywhere in the solar system. It would settle which origin story is true, because the orbit's shape carries the signature of how it got there. A captured rogue traces a different path than a native survivor flung outward by Jupiter. One detection, and decades of competing hypotheses collapse into a single answer. That answer is sitting in the data Rubin is collecting right now, exposure by exposure, night by night, in the high desert above the Atacama. We just haven't processed far enough into the survey to read it yet. That's the strange position science is in right now. Not ignorant, we've done the math, run the models, named the suspect. Not certain, we haven't seen it yet. It's the rarest place a field can stand, a known unknown with a known deadline. Think about what that actually means. For most of astronomy's history, discovery came without warning. Neptune appeared because Leverrier worked backward from Uranus's wobble and told astronomers where to point, but even that took a leap of faith, and the confirmation happened in a single night in 1846 because someone was willing to look. For most discoveries before and after, nobody knew what they didn't know until the data forced them to reckon with it. The unknown was genuinely unknown. Planet Y is different. We have a gravitational signature with a shape, a mass range, an orbital window. We have a telescope purpose-built for exactly this kind of search, already running, already scanning the same stretch of sky. We have a timeline, not open-ended, not someday, but a decade, maybe less. The uncertainty isn't whether we'll have an answer, it's what the answer will be. And those two outcomes are not symmetric. Ruling out Planet Y would mean the warp has a different explanation, some clustering artifact, some bias in how we sampled the outer solar system, some gravitational effect from the collective pull of Kuiper Belt objects we're still counting. That would be a genuine scientific result, but it would leave the 15-degree tilt unexplained and the question reopened with more pressure than before. Confirmation is something else entirely. A new planet in the solar system's inventory. The first in 179 years. That's not a number chosen for drama. Neptune was 1846. Everything since has been reclassified, demoted, or folded into a belt. No genuinely new major body has been added to the map in the lifetime of everyone alive and everyone who raised them. A detection would also mean the warp wasn't an anomaly, it was a message, and we read it correctly. That's a different kind of scientific victory than simply finding a planet. It would mean gravitational inference works at distances where direct observation fails, which opens every other stellar system to the same method. If our sun can hide a planet at 200 AUO, other stars almost certainly can too, and now we'd have a template for finding them. The orbit's shape would close the origin debate the same night. Captured rogue or native survivor, those two histories carve different arcs through the outer solar system, and the moment a confirmed orbit is published, one story ends and the other becomes true. So what Rubin is doing right now, exposure by exposure above the Atacama, is less like watching the sky and more like reading a sentence that's still being written. The subject is there, the verb is forming. We're waiting on the object, the one word that makes the whole thing land. Some questions in science take generations to even formulate. This one is formulated. The instrument exists, and the clock is running. That's not impatience. That's the edge of a discovery, and it is genuinely rare to know you're standing on it.